I'm Dr. T, and welcome to my office. This is a Q&A video, and these questions come from class discussion board, specifically my Survey 2 board, as of around 3 o'clock, April 2nd, 2020. Okay, so I've got 4 questions today. First one is, how are nucleic acids structured? Okay, so DNA is a double helix. It can have a couple of different windings for the double helix, but in general it's going to be a double helix, which means you've got 2 spirals and they're kind of back to back. I'll try and put an image over here that I pulled from Wikipedia. RNA can get a couple of different structures. You can get a single helix. That's fairly common for things like mRNA. Transfer RNA gives you what's usually referred to as a cruciform structure. It kind of looks like a cross shape, but that's really only if you look at it in 2 dimensions. The 3-dimensional is kind of more like a bent L shaped, so it's kind of, this interesting 3D look to it. Ribozymes, any of those are going to be weird shapes, just like the enzyme cousins. But yeah, so that's going to be your major structuring. The major one you're looking at, DNA is a double helix, and that's basically always going to be that way, except for when it's in the process of being read or something weird's happening, in which case the helix does get split apart, but that's usually when it's being copied or being read. Okay, next one. Why do different DNA sequences show up differently? Okay, this is missing a little bit of context, so this depends entirely what you're doing. So in the case of like an older DNA fingerprinting, in that case, DNA is chopped using a restriction enzyme, and then the chopped up DNA is separated based on size, going through an agarose gel, and then you use either a fluorescent or, in the really old school, a radioactive marker that would attach to the DNA. Other approaches you can get DNA to show up differently. There are DNA arrays where you have on essentially like a microchip, although this isn't a computer-based one, little tiny spots that have little bits of DNA that have been 3D printed onto it. And then those will complement to other bits of DNA floating past them. And then you can do things like fluorescent labeling, etc., to see what sticks where. This can do a ton of work there. You can do this with RNA as well. This is definitely one of those, I would say up and coming, but it's been up and coming for a long time. So it's very much an established technique. But it's one that's, 20 years ago was pretty rare to the best of my knowledge. So you can either do some kind of separation on size, or you can do some kind of complementary strand that complements to it and sticks. What was Human Genome Project? There's a couple of great videos. I'll try and find a link for those. Basically, it's to figure out the genetic code for humans. So all the A's, T's, G's, and C's, and then figure out what on earth those went to. And you can go look this one up online. Thankfully, the public project succeeded, and not the private one. The private one was going to copyright it. And as we all know, copyrights last, I think they're like 95 years, but in reality, it's like forever less a day because, they keep getting extended over and over again. So in that case, you'd have to pay this one company to use it. But hey, they didn't get it. They didn't copyright it. It was paid for by public dollars, so it's public domain. So yay, that was good. Anyways, so yeah, that was Human Genome Project. This was, the 90s. It was a wonder of the world. One of the spin-offs to Civilization actually put it in as a wonder of the world. That's a video game, by the way. And yeah, now we can do individual genomes for a few $100s. Technology has changed. And it's really kind of cool stuff. Okay, a last question. What is the extracellular matrix? So this is the space between cells. So if you look at a tissue, not all of the tissue is made of cells. Some of it, like classic one, is a bone. You've got collagen, and then it's got calcium phosphate. It's actually hydroxyapatite, just packed in there. This is the area between cells. This is the extra, outside of, cellular, outside the cell, matrix, and this is kind of the array of stuff between cells. So for humans, this is typically going to be a lot of collagen. If it's bone, that's going to have some calcium deposits with some other, usually calcium phosphate, but it varies. At least I think it does. I don't know enough about my extracellular matrix to say exactly what's in most of those. But basically, it's going to be collagen for humans with some calcium salts, mostly calcium phosphate. Plants, obviously, they're going to love themselves some cellulose. They really go in for the cellulose. So yeah, that was today's questions. If you've got questions, feel free to post them. If you're in one of my classes on the discussion board, if you're not, post them on a YouTube video. I read all the comments. So with that said, have a wonderful day.